right. Well, thank you very much for coming to our event today. Thanks. This event is organized by many people, and it's hosted by the Nuclear Engineering Department of UC Berkeley, and we're very excited to be able to have a real discussion at today's seminar, which is different, but really what academia is all about, having a constructive discussion about facts and data. And so what are the scientific certainties and uncertainties in our climate future is the title of today's discussion. It's going to be moderated by Bob Jacobsen here, and he's going to introduce the speakers in a minute. So thank you very much for coming, and hopefully we have a fruitful discussion in this topic. Thanks. Bob.
So I'm delighted to introduce our two speakers. Further from me is Steve Koonin, who's yes, we wave, who's been a professor at Caltech, has served as Undersecretary of Science in the Department of Energy in the Obama administration, and is now a professor at NYU. Most recently, he's written a best-selling book. I've actually seen a couple of copies in the room, Unsettled: What Climate Science Tells Us, What It Doesn't, and Why It Matters, which addresses issues of how science is presented and how people take away from it the messages they want to take. He holds a Bachelor of Science in Physics from Caltech and a PhD in Theoretical Physics from MIT. Closer to me is our own David Romps, who's a professor of climate physics in our Department of Earth and Planetary Science and a faculty science, and I have to read this, Climate and Ecosystem Sciences Division at LBNL up the hill. He studies the fundamental physics of climate and educates students and the public about global warming. He has a BS in math and a BS MS in physics from Yale and a PhD in physics from Harvard. And he teaches, oops, I just lost it, teaches the currently popular course, Introduction to Climate Change here. So welcome our two speakers, and I will turn it over to Professor Koonin. Let's go down the back.
Let's see if we can make this work. Okay. First of all, thanks for Peter, Bob, David, many other people who were instrumental in making this happen. I think it's really important to have a good discussion of some very important issues. Let's see, is this working? No, I'm going to have to use this, which is fine. Climate and energy are front and center today. This is some measure of the global temperature, and we know that it's gone up by about 1.1 degrees since 1900. At the same time, human influences on the climate are growing. I show you here the measurement of the concentration of carbon dioxide since 1960, and it's gone up from somewhat less than 300 now to 420 parts per million, exerting a warming influence on the climate. But the questions posed by this circumstance are pretty difficult. We'd like to know how and why the global and local climates have changed in the recent and distant past. We'd like to know how the climate is going to change in the future under growing human influences and natural phenomena. How will those changes impact ecosystems and society? And maybe the bottom line, what should we do about this? What's our response? And the response, as one starts to think about it and understand it, really have to strike a balance. On the one side, we've got the certainties and uncertainties in what we know about the climate, the hazards, the risks, and the benefits. There are benefits of a changing climate. On the other side, we've got a growing demand for clean, reliable, and affordable energy to sustain developed societies and to aid the development of much of the world. And that balance has to be struck by considering the efficacies and the costs of various responses, overlain with values and priorities, risk tolerance, intergenerational geographical equities. One can go on and on. It's not a simple subject, and one can write whole books, teach whole courses about how we strike this balance. David and I today are going to be concentrating just on the science part. We're scientists, and so have a particular thing to say about the left-hand box. But I would assert that there are some scientists, many institutions, the media and the politicians who have put their finger on the scale and have cooked the books in some ways about how the science is presented to non-experts. The science is often invoked. There's the president on the first day of his administration saying, we're going to follow the science. There's John Kerry, Special Envoy for Climate, saying, let there be no doubt in anybody's mind that the science is absolutely certain, etc., etc. There are a host of distinguished people, from Bernie Sanders, Mark Carney, who's an important figure in finance, Bill Gates, my friend Ernie Moniz, former Secretary of Energy, all using the words existential threat, climate crisis, climate emergency, climate disaster, when the most recent UN report on the physical parts of the climate science was released in August. Secretary General Guterres said, code red for humanity, billions of people are at immediate risk. And then finally, the Secretary of Defense, some months ago, almost a year ago, said, you know, this is an existential national security threat. I think in the last couple months, he's probably recalibrated what existential means. Okay? Nevertheless, you'll have all of these people saying this is really important, we had better act promptly. Well, where are they getting their science from? It's a big game of telephone. It starts with the observational data and the research literature, which are perfectly fine, and if you read it, it looks like any other field of science. It goes through assessment reports that are issued every 6 or 7 years by the UN, AR6, Sixth Assessment Report. The US government, every 4 years, issues its own assessment report. These reports are meant to survey, summarize, and package the science for non-experts. They do that in part through their summaries for policymakers. That goes out to the media and then to decision makers and the public. And there are ample opportunities for bad behavior in an intellectual sense as you go through this chain. You confuse weather with climate, you take implausibly extreme scenarios for future emissions as business as usual, you minimize uncertainties, etc., etc. I got so annoyed by this disconnect between what's at the beginning of this chain and what's at the end that about 3 years ago I decided to write a book which tries to circumvent this and show, obviously you can't cover everything, but show people some of what's in the reports. And everything I'm going to tell you, everything I put in the book is either in the reports itself or in the original research literature. So I'm going to say some words about models and then give you some misrepresentation vignettes, hurricanes, sea level rise, etc. So we have many models for climate science, but the ones that are given the most effort and most prominence are general circulation models that cut the Earth into many hundreds of millions of voxels and then use the laws of physics to move matter and energy between the voxels. These are important. They help us understand how the climate system works, how it has changed in the past, and how it might change in the future. But when you think about it, this is an absolutely heroic task. And, you know, people like David, I think it's wonderful that they're giving their best effort to it, but there are real challenges. The computational burden, there are 10 to the 8th voxels. The size of the voxel is 100 kilometers on a side in a modern GCM. Time step is 10 minutes, and you've got to step it through centuries in order to exploit the model. The grid size is much too large to describe many weather phenomena. Think thunderheads, for example. And so you have to make assumptions, so-called subgrid parameterizations. Also, the fact that the atmosphere is thin means that the aspect ratio of the voxels is very high. They're typically about 100 times as wide as they are thick, and that makes it very difficult to deal with turbulence, which is very important in the transfer of energy from the surface up into the atmosphere. There are emergent feedbacks. For example, when it gets warmer, the ice disappears, makes the planet a little bit more reflective. These are not things you can put in from first principles, but need to be parameterized. They enhance the sensitivity by a factor of 2 or 3 over what you would expect without them. These need to be tuned. Human influences are at the 0.5% level, about 2 watts per square meter of energy flow, whereas the sunlight, infrared radiation are a couple hundred watts per square meter. So you're looking at the response to small perturbative effects. There are many knobs that can be tuned, and they are tuned, whether it's convection, clouds, snow, and ice mixing in the oceans, and so on. And then if you're going to try to simulate the real climate, what was the ocean doing 100 years ago? We don't know. So you have to make assumptions. And maybe even to make it worse, there are multi-decadal modes of the system. Here's one example constructed from the actual data of oscillations extending over 60 or 70 years in the properties of the North Atlantic. The models neither get these right in timing, magnitude, or phase, pattern. So it's pretty tough. And then finally, you've got this degeneracy between greenhouse gases which warm and human-caused aerosols which cool. They are of the same magnitude, although the warming is larger. And of course, you have to parameterize the aerosols, and so there's some significant uncertainty. Here's a graph from a relatively recent paper where they show how the most recent generation of models do or do not reproduce the temperature history over the last 120 years. The black line is the observed temperature, and the different traces are the different models. There are about 50 different models. They've been sorted here according to their sensitivities, and you can see that some of the models produced by the best modelers on the planet are much too sensitive to growing greenhouse gases. You can quantify the sensitivity. Here's a collection of 40-some-odd models, and you can see that about 40% of them have been deemed to be much too sensitive. So it's a little bit disturbing that we make our best efforts and we still produce models that are just way outside of what's physically plausible. And in fact, Tim Palmer and Bjorn Stevens, writing a couple years ago in PNAS, said, for many key applications, the current generation of models is just not fit for purpose. Of course, what the community does is average these models, maybe throwing out some of the more sensitive ones, saying that's what the real world will do. Let me turn to some data and historical data. You might be surprised to know that very little is happening with hurricanes. This is a graph since 1970 of the number of tropical storms and the number of hurricanes, and you can see over 50 years, not much going on at all. Ups and downs, perhaps. You can look at a different measure of hurricane activity, which weights the stronger storms by the square of their velocity, and again, you see large ups and downs, but no trend. And that's, in fact, in the reports. The US government report in 2018 said we've got low confidence in any multi-decadal or centennial trend. In 2019, there was a paper by 11 hurricane experts in which they gave their own individual opinions, and again, nothing much happening. We couldn't detect anything. In the most recent IPCC report, low confidence in most reported long-term trends in tropical cyclones. There's a little bit of a story behind that, which I'm happy to go into in the questions, where there is one metric which seems to show a trend, but then there have been more recent papers that say not so fast. If you listen to CNN or any of the broadcasts or read the New York Times, you would never know this. Talk about sea level a little bit. Sea level has been rising for 20,000 years. This is a Berkeley-generated graph. Robert wrote it from Berkeley Earth, which shows the geological record of sea level since the glaciers started disappearing about 20,000 years ago, and it went up by about 120 meters or 400 feet. Right? You can see that it slowed down starting about 8,000 years ago, but it's still been going up. And so the question is not whether sea level is rising, which is all you read about in the papers, but in fact, has it accelerated since 1900, The discussion hinges on tenths of a millimeter per year differences. To what extent is the acceleration human-caused? And of course, what's going to happen in the next few centuries. Again, you can write a whole book about this. I'm just going to show you one example. The most recent UN report contains a set of projections for what sea level is going to do, depending upon what emissions are going to happen over the next many years. I live in New York City these days, and so I've gotten really interested in the sea level at the Battery, the southern tip of Manhattan, where there has been a tide gauge for 160 years. And this is the rate of rise in millimeters per year. You see it goes up and down. Even as human influence has been growing, it's not going up, obviously. The IPCC projections, which you can pull off the NASA website, depending upon emission scenarios, all go up like that, but with enormous uncertainties. NOAA, in a report released a couple months ago, said it's locked in that the sea level is going to rise a foot in the next 30 years. And so, independent of model, independent of emission scenario, they say that this curve is going to go up to that red star with about that uncertainty. We shall see. Meanwhile, you've got credible consensus scientists saying that the use of these models is just unwarranted to guide adaptation. They're just not precise enough. Nevertheless, when the report came out, disaster. All right. People don't understand that climate plays out over decades. I like this chart. The record of the Nile, summer minimum in Egypt over almost 1,000 years. Annual values. The blue are the annual values, and the red is the 30-year average. And, you know, if I were a medieval Egyptian, I'd probably be listening to some climate panel around that time saying, new normal, new normal. We just need to pray a bit more and do some sacrifices. And of course, if they had just waited a couple hundred years, it comes back up again. Obviously not under human influences. We're doing this today. NASA in 2006 says Lake Victoria's waters are falling. That determines this. And then 2021, Lake Victoria waters are rising. 30 seconds more, Bob. I'm just going to do one more. We do it today as well. Here's The Guardian in December 2019 saying Greenland's ice sheet is melting 7 times faster than in the 1990s. The scale and speed of the loss is much higher than predicted, threatening inundation for hundreds of millions of people. Well, about a month ago, I published the actual data in the Wall Street Journal, one of the recognized data sets. That's what it looks like. This is the annual melt rate in gigatons. Yes, it did go up a lot then, but somehow they forgot to mention it went up there as well, when human influences were 1/5 as much. This has got very little to do with human influences. It's about long-term weather patterns in the North Atlantic. Nevertheless, the Guardian is scaring the bejesus out of people. All right? That's the thumb on the scale. There are many other examples. Maybe I'll get a chance after David talks to go through a few more of them. Okay, thank you. David.
Well, I need just a second here to plug in. This is where ideally someone would play the piano and entertain people. My apologies for the time needed on the switch here. Great. Okay. Thanks for bearing with me there. So I think it's safe to say that Professor Koonin and I have different objectives for this event. Professor Koonin thinks that global warming is not a big deal, and he wants to convince you of that too. I, on the other hand, think that global warming is the biggest deal, but contrary to what you might expect, I'm not going to try to convince you of that today. Instead, my objective is to tell you what I've learned by reading through some of Professor Koonin's work. So I've dug into his work and tried to replicate his claims and figures. And along the way, I've discovered that there are a few techniques that I have to use over and over again to reach the same conclusions. And these are some of the techniques that have been used by the climate denial community for decades now, to stymie action on climate. So I think it's useful to know about them. And I'm going to tell you about them not in the hopes that you use them, but that you can then instead identify them when you see them being used by others. I am, however, just for the sake of framing, going to present this as a how-to tutorial. But again, it's not to encourage you to use these techniques, but again, to be able to identify them. So let me back up first and explain that there are 3 broad strategies that are used to delay action on climate, get people confused. So one of them is just hardcore climate denial. This is where you deny that the planet is warming, or you deny that humans are responsible for the warming. This was popular in the 1990s, and some intrepid individuals got some mileage out of this into the 2000s, even 2010s, but these days it's not used because it's not credible. So instead, there are 2 other strategies that are now in vogue, which I call Pupoism and Doomism. Pupoism is where you poo-poo global warming. You downplay the seriousness of the issue. You make fun of it. You make light of it, et cetera, to try to convince people that it's not a big deal. Now, I want to be clear. Whether or not you think global warming is a big deal is a product of 2 things: your understanding of the scientific facts and your values. And if you're out there giving a fair and accurate portrayal of the science, but your values tell you that you don't care and you don't think others should either, that may mean that you're not a very nice person, but you are acting with integrity, and I wouldn't put you in this category. Instead, if you're out there giving misleading or inaccurate portrayals of the science as part of an effort to get people to believe that it's not a big issue or an important issue, then that's what I'm referring to here as Pupoism. Doomism is where you accept that humans are warming the planet. You may even accept that it's a big deal, but you say, oh, shucks, it's too late or too expensive to do anything about it. So we should just capitulate, roll over, and sit on our hands and not take any substantive action. So to figure out where Professor Koonin might sit on this spectrum, let's take a look at some of his quotes. So Professor Koonin says that humans exert a physically small warming influence on the climate, which is a bit of Pupoism. Or stabilizing human influences on the climate is a practical impossibility, which is a bit of Doomism. Or the impact of human influences on the climate is too uncertain and very likely too small to warrant action. Again, Pupoism. There is no crisis. Global warming is going to be a bump in the road. This is not going to be a big deal. And we can adapt to almost any temperature. So it's a collection of Pupoism, also some Doomism, but I think primarily this is about the former. So I want to go into some of the techniques that are used to poo-poo global warming. The first and most important, I believe, is this art of cherry picking. You want to cherry pick the data set. You want to cherry pick the geographical location. You want to cherry pick the time interval you're looking at to make the case. You can also play up or down the uncertainties depending on which one is to your advantage. You can use a noisy statistic. This is really helpful. I mean, if I just show temperature, you'll see temperature rising, and that's not very helpful if you're trying to poo-poo the issue. But if you use some other derived statistic, like the rate of change of temperature, or the variance of temperature, or the rate of new records of temperature, those are noisy statistics that will not, when presented, have the be as evidently connected to global warming. You can take derivatives. If some observable has gone from here to here, if you present that, they'll have the appearance of there being a global warming influence, in which case, many cases, there will be. But that's not helpful if you're trying to poo-poo the issue. So you could take the time series, and you could take the derivative of it. And now you get this wiggly thing. And it looks like things have been wiggling forever, and they're just wiggling now. And so there's not an issue here. You can even take a second derivative, as we'll see. And finally, you want to ignore the counterfactual. The counterfactual is what would have happened in the absence of global warming. It's by comparing our best guess of the counterfactual to what actually happened that allows us to see what the effect of global warming was. Very often, you're not going to want to show that if you're trying to poo-poo the issue. Okay. Now, my English teacher told me, David, show, don't tell. So I'm going to show how to use these techniques by working through an example. Okay, let's say we want to write an op-ed in a newspaper to poo-poo global warming. And we want to title that op-ed something like, "Something's melting ice is no cause for climate change panic." How are we going to proceed? Well, first, we're going to want to cherry pick. We want to figure out which melting ice we're going to be looking at here. So let's look at a map of the change in temperature over the instrumental record over the Earth. So here it is. I've taken the instrumental record, 1895 to 2018. I've split it into two halves, taken the mean of those two halves, and taken the difference. So this is the change in temperature between those two halves over the Earth. And you'll notice, yeah, global warming, obviously. But there's also a spot that hasn't warmed. It's the well-known warming hole in the North Atlantic. This is associated with a slowdown in the current of warm waters northward in the Atlantic. As that slows down, which is a robust feature of many GCMs when put through a global warming scenario, then it actually leads to a cooling of the North Atlantic. And what's up in the North Atlantic, adjacent to this warming hole, is Greenland. So Greenland's where we're going to want to go to talk about melting ice, certainly not Antarctica. We'll want to go to Greenland. So if we go back to our title, we're going to want to say Greenland's melting ice is no cause for climate change panic. Now, we can't just say that. We need to present some data. So let's take a look at the data. We want to make a figure for this op-ed. So here's some of the data. This is the ice anomaly on Greenland in gigatons of ice. And I'm showing here two different reconstructions just to give you a sense of the uncertainty. I'm using Mankoff's discharge and basal mass balance for both. I'm using Hanna's surface mass balance instead of Mankoff's in the red curve there. So you see, there are some big uncertainties here. Right? These two reconstructions differ in the details, but they both agree that a lot of ice has melted off of Greenland, trillions of tons of ice. So this is not the kind of figure we're going to want to show to make our case that global warming is not a big deal. This will not be helpful. So what do? Well, we can use another one of our techniques here, which is to take a derivative. If we take a derivative, we can plot not this series, but the difference from year to year in these time series, which will be a lot messier. So let's do that for both of these reconstructions. And there we go. Oh, it's a great, big, glorious mess, isn't it? And I've added error bars to here from the original data sets. But so it's a mess, for sure. And you certainly can't publish this in a newspaper because it would give people a headache. So we've got to smooth it. So we'll apply a 10-year smoothing average to this and generate some more enjoyable to look at curves. So here are the two curves. Remember, this is the first derivative now of the ice anomaly from the red and blue data sets. Now, if I look at these two curves, there's one of them I do not like. One of these appears to have kind of a trend, this red one. It starts down low, and then it goes up high. And this is not good for us because that, again, evokes some notion of warming or change. So what we can do is we can cherry pick our data set. We can throw that one away. This one has more wiggles, which is good. Now, if I look at this curve here, one of the problems with it is that the error bars are big. I can drive a truck through here. I can practically put a flat line through here within the error bars. And that won't be very helpful if I'm trying to convince people that this thing has been wiggling consistently for a long time. So what I do is I can play down the uncertainties. I can artificially reduce the error bars. And you might say, David, well, how can you do that? You can't just change the error bars. But the neat thing is that if you're submitting to a newspaper, the editorial staff don't ask you how you calculated your error bars. So you can get away with a lot of things here, including just reducing them like this. OK, so now we've got smaller error bars. We've got more wiggles that look like they're quite certain. But I'm still not a big fan of this from a poo-pooing perspective, because it still looks like there's a trend. I have low values in the beginning, higher values towards the latter part. So what do? We use another cherry-picking technique. We will simply throw away the first 50 years of this time series. And that leaves us then with this, which is pretty good. Only I don't like this reference line being here because it reminds me that this is all melting. Greenland's not gaining anything. It's melting consistently. So let's throw away this reference line. So it's gone. And now we've got a pretty good curve. We look at this and we see that there have been wiggles throughout time. The wiggles now are the same as the wiggles before. This is fairly compelling, but we can do even more. We can take another derivative. If we look at this data set, which is, remember, we've used a 10-year smoother to this. If we look at this and we stand back and we squint, we see that in the last several years, the slope of this first derivative is sort of kind of negative. And that sort of kind of negative second derivative is a wonderful thing for us because it allows us to add a subtitle to our op-ed. Instead of just Greenland's melting ice is no cause for climate change panic, we can now say the annual loss has been decreasing, negative second derivative, in the past decade, even as the globe continues to warm. It sounds like we've got a major contradiction here. So indeed, as Professor Koonin mentioned, he published a piece in the Wall Street Journal. Here is the same exact figure from the same exact data right here. The casual reader looks at this and says, this thing has always been wiggling. The wiggles now are the same as before. And oh yeah, look, it's coming down. Whatever this thing is coming down when it should be going up because we have global warming. So this is, I would say, quite a masterpiece. But what's the real story here? The real story, of course, is that Greenland has lost trillions of tons of ice. And we know as we continue to warm the planet, we're going to be driving Greenland to lose even more ice. So that's the story. And I want to impress upon you, Greenland is a big place. It has the same area as the West, from California to New Mexico up to Montana, over to Washington. It's an enormous ice sheet that has, over its entire surface, lost an average of 10 meters of ice. So you can just imagine, over the entire western United States, an ice sheet that's 10 meters thick, as tall as a 3-story building, that has since melted and gone into the sea. More worryingly, we think that we are approaching, or maybe even beyond the point of no return for the Greenland ice sheet. And that's quite disturbing. It means that the amount of warming we've caused is getting close to, or approaching, the amount of warming that will eventually, could eventually doom the Greenland ice sheet to losing most of its mass. If it did lose all of its mass, of course, that would raise sea level by about 7 meters, or about 20 feet, transforming the planet. So I'll stop there, and if we have time, I can go through other examples. Thanks. Do you need the?
Yeah,
Okay, very good. There you go.
So while we're getting hooked up,
I'm just going to move this one last chair.
I think David said a couple of things that are not quite right and omitted a couple of things. First of all, I didn't pick Greenland, okay? The newspaper picked Greenland. They misled you. They focused on the rate of change, not I. And when you look at the actual data, it's very different than what the Guardian said. Second, I don't think I artificially reduced the error bars. There's a long exposition which I posted that described how I handled the uncertainties. Standard statistical way, square root of n reduction in the mean. And so I don't know where you got your error bars. The third, what David didn't tell you, is that the roughly 10 trillions of tons of ice that Greenland lost over the last century accounted for all of 3 centimeters of global sea level rise. Hardly anything to get alarmed about. And so it's pretty clear that human influences aren't driving Greenland, at least at the moment. I want to, how do I get this to come back? Good, all right. On the issue of poo-pooing, you know, it's not I who poo-poo, but it in fact is the IPCC who poo-poo. And let me just show you that. I want to talk about the economic impact of warming. U.S. Climate Science Special Report, or National Climate Assessment, says climate change is projected to impose substantial damages, hundreds of billions of tons of dollars by the end of the century if we don't do something dramatic. And they give us this chart by economic sector and to 3 significant figures of how much economic impact there's going to be in 2100. And you can see it is hundreds of billions of dollars, okay? Made the media All right. Even Fox News said climate report warns of grim economic consequences. When you look at the chart that they give you in the report, it shows for temperature changes of a few degrees, a few percent impact on the economy in 2100. You can scan the literature and come up with a similar thing for the globe, a few percent impact for a few degrees. And in fact, if you read the IPCC, they say the impact of climate change will be small relative to the impact of other drivers, right? Demographics, development, etc. And in fact, if you ask what a 2% or 4% impact in 2100 would be on the US economy, it is a couple years of delay, 80 years from now in growth, all right? So I would say, in fact, is this the climate crisis? I'm not poo-pooing this. The IPCC just did not put things in context, right? Let me close with a couple of remarks, and then I'll turn the stage back over to David. We must not Gruberize climate science. And what do I mean by that? Jonathan Gruber is a professor at MIT. He was one of the principal architects of the Affordable Care Act. And at one point, after it was all over, he said, lack of transparency is a huge political advantage. It was really, really critical to getting the act passed. At least one key provision was a very clever basic exploitation of the lack of economic understanding of the American voter. I would assert that the same thing is going on in climate science due to a few scientists, the institutions, the media. When we misrepresent the science to persuade rather than to inform, we usurp the right of the public to make informed decisions. We distract from more urgent needs, and boy, do we have many of them. We tarnish scientific input to other matters, and then we depress young people. Many young people I talk to have been depressed because we have over-egged the custard. And so we need to take our thumb off the scale by talking fully and completely about the certainties and uncertainties of the science. If I could give a prescription, we need to cancel the climate crisis. We need to acknowledge the task and the challenge of reducing human emissions. But energy is so central and so intertwined with systems that if we take precipitous climate action, it's a far greater threat than anything you can imagine with climate change. We need better observations, better understanding. These assessment reports really need to be scrubbed. I gave examples in the book. I've given you some examples in the media of how they misrepresent. And it would be great if people like me would sit down with people like David, go through those reports, and make sure that they give a transparent, complete, and unbiased representation. For example, like 10 trillion tons is 3 centimeters of global ocean rise. Okay? Thank you.
Uncorrelated, statistically independent. And in fact, that uncertainty is in large part due to uncertain bias. And also we saw, for example, the difference between the two reconstructions. There's big structural uncertainty in those models as well. Okay, so since Professor Koonin mentioned sea level rise again, I think maybe we can do another example involving sea level. Let's see here. Nope, that's not where I want to be, but I'll get there very soon. Okay, so imagine we want to poo-poo global warming by talking about sea level rise. So we want to say something like sea level rise is not a big deal because blank. Well, what's the blank going to be? What are we going to say about sea level rise that minimizes this issue? Well, if we look at the data from the past 30 years, These are multiple different reconstructions showing the rising sea level. This is clearly not a helpful plot for us to show if we're trying to minimize this issue. So what we can do instead is we can zoom out. So let's zoom out. This is 30 years. Let's zoom out almost 100 times more and look at the past 2,500 years. I'm showing one reconstruction of sea level here. There are a few different reconstructions of sea level. This is just one of them. They all kind of wiggle like this. It's a general idea. But this is also not a very helpful plot to show if you're trying to minimize the impact of global warming on sea level, because we have this unprecedented rise over here on the right-hand side, which is actually even off this chart. So this is not a helpful plot to show either. But what we can do is we can cherry pick the time interval that we're showing. So if we zoom in here, we can see that the rise in sea level began around 1880. Right? This thing had been rising and falling, rising and falling. It just so happened it was rising in 1880 before there was significant human influence on sea level. This is a great thing for us because now we can say it's always been rising. Now, what you don't want to do is show the counterfactual. The counterfactual is what would have likely happened to sea level if we hadn't had global warming. And of course, we can't know this with great certainty, but a best estimate would be something like this. It's from the Computational paper. So it's that difference between the counterfactual here and the actual up there that is the signal of global warming. It's our best estimate of the magnitude of the impact of global warming on sea level today. But of course, we don't want to show that. It's an important tactic down here is to ignore the counterfactual. So sea level rise is not a big deal because it was already rising. That's what we want to say. And if we go to Professor Koonin's book, here's a plot of sea level starting in that golden year of 1880. And what do we say about it? We see sea level was rising at the end of the 19th century, well before there were significant human influences on the climate. Now, this is what I'd say the real story is. The real story is that, well, sea level rise is slow. Professor Koonin mentions the 3 millimeters per year. That's, it's a tiny amount. And the reason why this is all so slow, in part, is because ice sheets take about 2,000 years to equilibrate to a new climate state. So they're very slow systems to respond. And so if you don't care about other people, this is the fact that should tell you you shouldn't care about sea level rise because it's someone else's problem in the future. But if you do care about other people, the fact that should make you potentially concerned about sea level rise is the fact that sea level rise is big. And I mean big in the sense that once things equilibrate, we commit to something like, big uncertainty here, something like 10 feet of rise per sustained 1 degree Fahrenheit temperature increment. Big uncertainty here, I'm getting this number by taking our current sea level and amount of ice and temperature, and then looking at, we have a general idea of what temperature we have to go to melt everything, and what the sea level rise would be when we do that. And you can connect those two dots, calculate the slope. That's about 10 feet per degree Fahrenheit. But again, big uncertainty on that. My point is that it's a fairly substantial number. So if we sustain temperatures at 2 degrees Fahrenheit, a reasonable guess as to how much committed sea level rise we might get is about 20 feet. It could be much smaller, it could be much bigger. Professor Koonin could certainly find papers that say it's much smaller than this, and I could find papers that show it's much bigger than this. There's big uncertainty. And while sea level rise might be slow, the rate at which we are committing the planet to higher sea levels is fast. So using this relationship, we're adding something like a foot of committed rise to the ocean every 3 years. Again, big uncertainty, could be 2 years, could be 5 years. But this is the rate at which we're committing the future Earth to a higher ocean is quite fast, quite rapid. To give you a sense of what 20 feet of sea level rise looks like, this is the Bay Area. It's hard to see, I'm sure, in the back, but a lot of the area fringing the bay has been inundated. And for those who aren't native to here or don't live here, this is not a feature that exists today. This would be a new inland lake, causing major problems for Sacramento up there. If we were to, continue on the, sit on our hands, continue to burn fossil fuel, we just burned all of the available fossil fuel, this is what the landscape would look like. San Francisco becomes an island. The Central Valley becomes a central sea. So this is the direction that we are heading in if we just continue to go along and say, well, each increment is fine. We'll just keep adding more and more and more until we've done it all. At this point, the bay is lapping up at about Oxford Street, the west edge of campus, and most of Berkeley is gone. NYU is well long gone before you get to this point. This, of course, is an extreme scenario. And Professor Koonin will point out this is an extreme scenario. We're not doing this anytime soon. But we're headed in this direction. OK, I will stop there.
We have time for a couple questions, and we have some microphones, because I believe that there's some people who are live. Why don't you guys pull over the chairs?
Oh, yeah, let's get a chair or two.
And, let's see. Thank you.
As nuclear engineers, we're sensitive to the use of extreme scenarios. The very first nuclear safety study said we were going to lose Detroit. That the small reactor was going to completely destroy the entire city, since then, we nuclear engineers have come to see a lot of psychology, the psychology of fear, and that the fear that you have from a hazard depends not on the probability of something happening or the overall likelihood, but how graphically you describe the worst possible outcome. So I'm wondering, can you tell us why you ended with an extreme example that is actually not possible, because we can't burn everything, all the carbon on the Earth's crust?
Sure. That wasn't a scenario in which we burn all of the fossil fuel that's in the crust. That is an impossible undertaking. That is a scenario that is a very, very plausible scenario if we were to burn about 5 teratons of carbon that's available to us in oil, gas, and coal, primarily in coal, which, of course, as you know, can be liquefied to... what's that?
Per year.
No. We're burning carbon at 10 gigatons a year now. So we're talking about 5 teratons. It's something you wouldn't do tomorrow, you wouldn't do next decade, you wouldn't even do this century. But if we continue the way we are, you can get quite a good way there in 2 or 3 centuries. So yes, that is us continuing on the kind of do-nothing path that Professor Koonin seems to be advocating, but out over a very long time.
So let me first of all, you keep saying I advocate do nothing. No, I don't do that. What I advocate is that we think through how we're going to do this with due consideration of other people, such as the 3 billion people in the world who don't have adequate energy right now. Let me say a word about extreme scenarios. There was a meeting in 2012 in La Jolla, hosted by Michael Bloomberg, Tom Steyer, and so on, and this was in the New York Times, so it must be right, where they agreed to portray the most extreme scenario that the IPCC wrote down as business as usual. And you find that running through the reports and the research literature until about 2 or 3 years ago. People said, this is not going to happen. A reasonable projection of future emissions is more gradual than that. And so that's a good example of a manipulation of the scientific process by non-scientists to heighten alarm.
Carl, and then we'll go over there for the next one.
Thank you. Is it on?
Yes.
Good. So I wanted to ask a question precisely about the process of science. And I remember about 15 years ago, I was at Livermore at the time, and I remember hearing a talk by Susan Solomon, who was on the IPCC at the time. And she said that, the thing that surprised her was the fact that the most virulent critics of the IPCC were in fact the environmental community who attacked them and said, look, you're confusing the public with these error bars and uncertainties and so forth. And you should really be sort of, charging, the ramparts and sensationalizing this because you people have credibility. You can put the brakes on this. And she gave an answer I respected. She said, no, we are like baseball umpires. We're calling strikes and balls. We call them as we see them. Now, you guys are much closer to the process than I am. I don't know, maybe you were on the IPC or not, but I get the impression over the years that of the large number of people on the IPCC, which might be 1,000 or so it's hundreds of people, I guess, on
400 in the most recent working group one.
I get the impression that they actually all go into doing their science with a strong a priori point of view. As a scientist, I know for a fact you have to have a point of view, whether you're doing cosmology or nuclear physics, whatever. All scientists have a point of view, and in fact, it's good for science to do so. I worry, because some of the things I read, leaks and so forth, that points of view end up, doing curation of how data is presented. And I worry that from the time that Susan Solomon was on it to now, that is happening. Just tell me a little bit about the process. Is it really true that everyone on the IPCC has that point of view going into doing their science?
So let me try first, since David went first before, and then he can have his say. First of all, science is cumulative, and we certainly understand more now than we did back in the late 90s. So there are some things that are certain. When you read the IPCC reports, by and large, they are reasonable summaries if you read them, not the summaries for policymakers, but the reports themselves, which is 3,949 pages in the last UN report, all right? Took several years to write and so on. They're not bad, okay? They have gems buried in them that somehow never make it down that game of telephone. Do people go in with a point of view? I think many do. Again, I know people who've been involved with the process and say the question is, well, what are we going to write to make the most extreme case? But when you read the reports themselves, they're not bad. It's just that the countervailing points in the reports don't come through. For example, in Greenland, the most recent report on Greenland melting says there's high natural variability in the melt rate, which you can obviously see in the data. And the research papers, which they cite, say it's not clear we're going to see an emergence of a human signal for at least a couple decades. Right? But nevertheless, the Guardian says, wow, it's all melting. And so, all right, that's enough.
Well, I think I largely agree. Good. I mean, the IPCC reports are the best attempt to summarize the peer-reviewed literature. So projects have to go through peer review, of course, to get published, but that doesn't mean that garbage still doesn't get through. Garbage does get through. But then the IPCC collects experts who then assess the stuff that's been put through peer review to come up with the most accurate portrayal they can of what the community as a whole thinks about the science. And so in that regard, I think it's a very helpful exercise that many people, hundreds, thousands, if you include multiple working groups, volunteered their time to do. It's a really heroic effort.
We have a mic there.
Yes.
Is that on?
Yeah, I think it's on. Yeah, hi. So it's so wonderful to have two scientists with opposing points of view at the same table. It's amazing.
Welcome to Berkeley.
I hear both of you speaking about the same literature and also speaking about the actions that we should be taking. So I am really curious to hear on which points you do agree with regards to the actions that we should be taking today.
Well, I would have to know what
okay, let me
Professor
try.
Koonin thinks
Yeah.
to know if I agree.
So there's a fundamental lesson from environmental economics that Bill Nordhaus won the Nobel Prize for in 2018. And here's the fundamental insight. There's an optimal rate for decarbonization. If we decarbonize too rapidly, we entail tremendous disruption of society because energy is so intertwined. and we deploy immature technology. If we decarbonize too slowly, climate risk, such as it is, grows. And I would assert that what's being proposed now, net zero by 2050, is both a fantasy, it's not going to happen, even the administration has said that, even by 2075, because you've got to provide energy for 3+ billion people, and the best way to do that, the most reliable and convenient way, is by fossil fuels. I said the dirty word, I'm sorry. And you've got to provide for those people. Meanwhile, we should be developing emissions-light technologies and map out a graceful decarbonization path that includes technology development, economics, regulation, and behavior. And if you do it too fast, it's all going to come a cropper. We've seen in the last couple months, energy security has suddenly emerged and everybody's thinking, right? So we got to deal with that even as we try to develop carbon-light technologies.
So what's hidden in these economic models that claim to give you an optimum path for decarbonizing is the objective function. It's the objective function they're trying to minimize or maximize. And in there, you have to weight future harm in some way, future damages. And typically what's done is that we apply a discount rate to future people. And this is a strange concept. Economists are very comfortable with it, apparently. It makes sense from a personal perspective. If you tell me that if I give you $100 now, you'll give me $1 million in 70 years, I'm not taking the deal because I won't be here. It does me no good. So I discount quite dramatically that future income. But to discount future lives is a quite different thing. And it's an implicit assumption in much of this. And so people use different discount rates. I use a very low discount rate for future lives. I don't afford them much less respect than I like to afford to people on Earth today. Now, I think what most of us would agree is that we have the technology to decarbonize something like 80% of the carbon emissions that we're putting out today. And so we're not doing that. We're not on the path to doing that, and nowhere near fast enough, in my opinion, based on my values and the damage that will be done in the interim. But Professor Koonin talks about needing to develop technologies and think and research. We need to do a lot more deployment as well, in my opinion.
So that'll be our last one in the back because we're running over on time, but I'm sure that people will stand around and discuss for a little while afterwards.
Again, I want to echo what Raluca just said about it's really great to see opposing viewpoints like this presented respectfully and coherently. So thank you to both of you. One bit of advice I would offer from the nuclear engineering side of the world is that when we have a process of post-publication review of data. You need this, okay? We don't design nuclear reactors based on a measurement that I did or that somebody else did that likely disagreed and had uncertainties that weren't equally quantified between the two. We have a nuclear data program. The IAEA works this, and that's the way we would design a nuclear reactor or a nuclear weapon or a production mechanism for a new radiopharmaceutical. This field needs this. It's people who are completely apolitical, who are just looking at data and making sure that the presentation is not done with a goal in mind. If that's done, you'll be able to have the raw data to be able to work with well. And there's going to be disagreements. You expect that, okay? And so you also will need a model, and the model will need to be informed by that. Now, it's possible that this IPCC work is doing part of this. I'm not sure, but it's very important that the folks who are doing this are impartial, left alone, and given free rein and support to be able to do that objective quantification correctly. That's just my one general bit of advice so that we can really follow through on this well.
Can I ask you just a quick follow-up question? Are we talking about the climate models, in particular the code for those climate models, or what?
It would be the data that those climate models are based on, and then the next extension is the model themselves. So for nuclear reaction data, we actually have an evaluation process that includes modeling. For nuclear structure and decay data, we don't. We just objectively report. I believe that there are two different components of data here, the raw measurements that you were showing, and then also the model extrapolated results. And in both cases, quantification requires people who are just full-time working just on that, and they're not the people who are actually doing the work. They're just reporting on the numbers and the uncertainties that are coming out.
Well, the good news is that the climate models are open source. You can download them, you can run them. The output from the climate models is available publicly. It's big. You have to have a big computer, depending on how much of it you want, but it's there to download and play with. And in fact, that's what a lot of us do, is we download that data freely and play with it. Yeah. Much of the observational data, in fact, I'm hard-pressed to think of observational data that's not open source and available to the public.
The problem is not at the head end of that game of telephone, okay? Data are curated. The models are, as David says, they're there if you want to. It's as you start to filter down and say, what does this mean for non-experts? That's where I think the corruption happens, and where some kind of external body. I advocated for a red team review because you can find all these mistakes and misleading statements in the summaries and in the media. Somebody needs to stand up and tell AOC, for example, the world is not going to end in 10 years, okay? Or John Kerry, that this is not the existential threat he thinks it is.
Do we have time for that one more there? Let's try and make it a quick one.
Okay. I just want to disagree with Professor Scarlett here. If it really is an existential urgent crisis, no, it's not a good idea to have endless debates about whether it's happening and having deniers, dialogue with deniers. So that's my comment. And I have a question for Professor Romps. What do you think of the coverage of climate change by mainstream media? Do you have examples of, it being exaggerated in terms of threats?
Oh, you can find examples of the media exaggerating or misreporting any topic, especially topics in science. So that's an easy one to do. And Professor Koonin has certainly highlighted some of those. I can tell you, though, that what bothers me about the reporting is, I mean, there are many things. Some of the exaggerations bother me as well, certainly. But what in particular bothers me is the lack of basic context that the news reporting is providing. We actually did a study on this here at Berkeley, looking at the New York Times coverage of climate change. And went and looked, we enlisted 12 undergraduate students to help pore through New York Times coverage of climate, and found that basic facts about the climate system were not being reported. In the beginning days, in the 80s, they would report the mechanism so that presumably the reader could understand what was going on and why. Nowadays, it's not reported at all. And you go and you ask the people, what causes global warming? And you get all sorts of answers involving the ozone layer or plastic pollution, even today, after this has been an issue for so many decades. So a lot of the context is not being reported in the news. Instead, they're chasing the shiny thing, the latest report, but then not providing the context in that resulting report.
So I would agree. I think the biggest thing that scientists need to do is enhance climate literacy and energy literacy. I teach both climate science and energy at NYU to graduate students, and when you expose them to the real literature, the real reports, whether science or technology, their eyes open up, all right? So I agree, context, complete context, really important.
And with that, let's call it a day.
All right. Good.